Ew. This YouTube here, or this movie, has very little to do with what the YouTube is about, which is namely Dr. Karl Space Lab. Let me see if I can get the yeah, I want to see what it looks like on the screen. But anyway, he's offering experiments, I think, for youngsters mostly, about what kind of experiments they'd want done on the INSS, which is the International Space Station. I'm not sure if they have any ideas for someone my age. I'm actually Fubbleduck, alias Roger Fancher, and I have some curiosities of my own. In continuation,
slow speed paper, slow speed paper, slow speed paper, slow.
How light and how light would an object have to be, and how much drag would it have to be able to survive re-entry? Basically, I'm thinking like a low density, high drag, and it seems like if the combination was right, then it should be possible for such an object to interface the Earth's atmosphere in such a way that it'll always be going slow enough for the altitude it's passing through to survive the punishment the atmosphere is dealing with it, which hopefully will not be that much. Now, drag obviously is a function of aerodynamic force, but I think frictional heat is a function of aerothermodynamic energy, and I think you can. Well, are they going to collide? No, I guess not. I'm pretty sure that you can go twice as fast on the same amount of drag in in 1/4 of the atmosphere. You know, because the form drag goes up with like a square of the speed. But the dynamic energy is actually proportional to the cube of the speed. So basically, you would, in order to go twice as fast on the same amount of thermodynamic energy, I'm pretty sure you'd have to be going like 1/8 of the atmosphere. In order, that makes it like a lot more critical and stuff. But I'm sure that there is a reduction in thermodynamic effects, because things don't burn up in low Earth orbit, and the atmosphere is not 100% gone there. I know that the force and thermodynamics are disproportionate, but I know I ended with but, and the thing behind the but is, I don't know what this thing is behind the but, because the but's behind everything else, that since you don't burn up at orbital speed and there's still some atmosphere left, it's obvious that you're not burning up by being in low Earth orbit. So it is quite evident that decreased atmospheric density not only decreases dynamic pressure, but also decreases atmospheric heating, just not quite at the same rate. The drag is reduced. And I hate not being able to see what it looks like through the live cam, but I'm there. Okay, I guess that's I mistakenly called it the blue Nibiru, but I guess it's the green Nibiru. That planet invaded inside the solar system. You know, I put in this caption that said blue Nibiru, but I guess it was a green Nibiru. Gee, must be a lot of chlorophyll on that planet. I hope it infertilates the Earth, creates new forms of vegetation. Hello. Hello, Mr. Planets. Anyway, continuing on, I think a good illustration would be the Lockheed SR-71 Blackbird, the reconnaissance plane. It goes about 2,000 miles an hour, roughly around 90,000 feet. And heating its skin temperature up to from 6 to 1,200 degrees Fahrenheit. Now, let's say you want to go high enough, to go fast enough. Let's say you want to go 4,000 miles an hour without making the skin any hotter. Going up high enough for half the atmosphere will not do it. Half the atmosphere of what it would be like at 85,000 feet. That would not do it. I mean, that wouldn't even, you'd still be over the same amount of drag. Going high enough to where the atmospheric density is a quarter that of which is at 85,000 feet will not do it. Although you would be able to go the same speed on the same amount of thrust if the same amount of thrust is available, which given the low density at that altitude is hard to say. In order to go 4,000 miles per hour in an SR-71 without getting any hotter, you would basically have to go to where the atmospheric density is about 1/8 of what it is at 85,000 feet. I do not know what's going on here. Looks like things are kind of seizing up here. I don't know if I don't know if it's still recording or not because the orbital simulation slowed down. I'll have to check it, but we'll see. Hopefully what I said will be captured way back to Earth. And if it's, there's probably a good chance that if it and the marker beacon and the homing device are slowly as a person under a parachute. Oh, are they gonna hit? Nope. They crossed again. The planets are getting weird. Moon and tiny planet mingle. Well, looks like the blue moon is trying to reacquire the purple planet. I guess it does that once in a blue moon. Marker beacon could be helpful in the indication of whether or not the package has survived. In case I haven't said before, obviously this would not be an experiment for inside the INSS. It would obviously involve the jettisoning of the package and, like I say, some kind of a marker beacon that it can be traced to wherever it sets down, and also obviously light enough to survive re-entry. It's the combination is almost certainly light enough to survive the landing, because it'll probably just be coming down